Our discussion of light as both a particle and a wave ends with electrons because now we're only concerned about how light is interacting with matter. Specifically, how is that light interacting with electrons? Electrons began to be treated like waves as soon as we realized, according to Louis de Broglie, that everything that has mass can be described by a wave equation. If you notice here, quickly in this math equation, wavelength equals Planck's constant divided by mass times velocity. If you have something that is very tiny in terms of mass, the bottom of that fraction becomes, well, mathematically, you're dividing by a very, 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 very small number, which makes the overall value skyrocket and get much larger in quantity. So things like electrons actually behave like waves more so than they behave like particles. Niels Bohr also contributed to our understanding of how these electrons behave as waves. Before de Broglie gave us the idea of matter as a wave, Bohr gave us this idea that electrons can only exist in discrete orbits called energy levels around an atom. We can kind of connect this back to de Broglie's idea because if we treat each one of those orbits like it's a standing wave, maybe orbit 1 is only 1 wavelength. Orbit 2 is 2 wavelengths, and so on and so forth. So the idea of electrons as waves lent itself to Bohr's idea that electrons are organized in those energy levels around the atom. A very important thing to understand, even though we know that the atomic model evolved beyond this, is that the types of light that we see when it is emitted by an atom comes from this idea of quantization, that electrons have the ability to get excited. And what does that mean? An electron can absorb energy, move to an outer energy level, it's unstable in that state, and then it immediately drops to some lower ring to release energy in the form of light. When we talk about the colors that we saw during our flame tests, sophomore chemistry, or when we analyze the atomic emission spectrum of elements, we're really viewing the action of these electrons as they get excited, drop back down to energy levels, and release light. And that light can be described by Planck's equation as a photon. Heisenberg's uncertainty principle also comes into play with how we describe electrons in atoms. We know that we can't measure simultaneously the position and the momentum, which is directly related to the energy of the electron, simultaneously with a high level of precision. So there has to be some give. And the give that we have here is position. We don't care exactly where that electron is. We care more about its energy. We want to describe its energy very accurately according to wave equations. So this is where Schrödinger comes in to give us our final piece of the puzzle in terms of our understanding of electrons as waves in an atom. So Schrödinger took these ideas together and created his wave equation for how an electron behaves. And this equation simply says that we can use some complicated mathematics to accurately describe the energy value of that electron in that given state. The solutions to Schrödinger's equation are actually three-dimensional, kind of like 2 + 2 = 4. Well, the answers that came out of Schrödinger's equation for the wave behavior of electrons gave us weird shapes based on electron probability, electron clouds. That's really the most accurate model of what an electron is. It's a wave, it's a standing wave that wraps around an atom three-dimensionally, and we don't know exactly where that electron is, but we have a threshold of 95% probability of where it is. The answers that came out of Schrödinger's equation actually had numbers, and these are called quantum numbers. N is the principal quantum number, and then we have the angular quantum number, or azimuthal quantum number, then we have the magnetic quantum number and the magnetic spin quantum number, which isn't represented in this chart. But we don't really use these numbers or notation because it's a little bit easier for us to use these terms that we've heard before, 1s and 2s and 2p and so on, to describe orbitals, subshells, and shells. And that's what we're going to do. We're going to ignore these quantum numbers, even though you should be aware of them when you take college-level chemistry For our purposes, we're going to focus more on these simple nomenclatures that refer to orbitals. You should know that s orbitals are spherical in shape. And these s orbitals get bigger if the principal quantum number gets bigger too. What does that principal quantum number determine? Think of that as the shell or the ring that the electrons are in. So the higher the principal quantum number, the further that the electrons are getting from the center of the atom, and the less likely it is to find them near the center of the atom. P orbitals, on the other hand, come in three different orientations. One p orbital is oriented along the z-axis, one along the x, and one along the y, and all three of these exist within one single shell. They start in the 2p, so you can have 2p orbitals. There's no 1p. There's a 3p, there's a 4p, so on and so forth. But in a given energy level, you can have electrons sitting in three different orientations along the x, y, and z axis. D orbitals come in sets of 5, and they have a cloverleaf shape. So our transition metals give us these electrons that are occupying these higher energy d orbitals. There are 4 different orientations along the different planes, and then there's this fifth one that kind of looks like a spaceship. But collectively, there's 5 different orientations for d orbitals around an atom. F orbitals get even more complicated in their shape, but there are 7 of them per sublevel within an energy level. We're going to use our shorthand notation to represent these complicated shapes. So we have electron configurations versus orbital diagrams. So each box represents one orbital. So instead of drawing a sphere or a dumbbell, we use these boxes to show where the electrons can be. The half arrows each represent an individual electron. The direction of the arrow is just telling us which way it's spinning. Is it spinning clockwise or counterclockwise, generating a magnetic field? So this is the longer way to represent electron configurations, which we learned in our sophomore chemistry class. The other way, which is a shorter hand notation, simply does away with the spins of the electrons, and we use superscripts instead. Each one of these is a subshell or sublevel. Each of the boxes is an orbital, and the big number in front of the letters tells us what energy level or principal quantum number those electrons are sitting within. We use the periodic table to help us remember the order that these orbitals are filled according to the Aufbau principle, which says electrons occupy lower energy levels before they start to occupy ones with higher energy. You can't have 2 electrons spinning the same way in the same orbital. That violates the Pauli exclusion principle. And we're going to quickly go over Hund's rule, right? We say that Hund described the process by which we fill a sublevel with single electrons per box before we start pairing them together. We can use the shape of the periodic table to help remember the order that these elements fill their orbitals with electrons. So let's do a quick warm-up. Let's see how much we remember in terms of orbital diagrams and electron configurations. So write the electron configuration for the element phosphorus in its ground state. What does ground state mean? It just means it's normal electron configuration, because remember, those electrons can be excited to higher energy orbitals. Then predict how many of its electrons are unpaired. Well, that's something you need to do by drawing an orbital diagram. So try to do those 2 things. I'll give you a second to pause the video. In its ground state, phosphorus has an electron configuration of 1s2, 2s2, 2p6, 3s2, 3p3, which means that it has 2 electrons in the first energy level, 8 electrons in the second energy level, and 5 electrons in the third energy level. Its highest energy electrons are in the 3p subshell. A more detailed picture is the orbital diagram of phosphorus. And if I draw that, my last subshell of electrons here, we can see, according to Hund's rule, I place them singly in each of these orbitals first, spinning the same way, which means that the only way to predict how many unpaired electrons it has is to draw this orbital diagram. So what is the pattern for the valence electron configuration for all of the halogens? If we just use the letter N as a placeholder for the principal quantum number in front of the subshell, whether that be S, P, D, or F. And then how many unpaired electrons does the element iron have? Let's see if we can figure this out. Pause the video, and then we'll go over the answer. Well, the pattern that all of the halogens follow, if we write its noble gas configuration, right, the noble gas followed by whatever the principal quantum number is of that period that we're in, S squared. If we're in period 6 and above, we have the energy level subtracted by 2. So if we were in period 7, that would be 5. F14. For periods 4 and above, it's whatever principal quantum number we're in minus 1, D10. But if we're only in period 2 or period 3, then it would just be NS2, NP5. All of the halogens have an electron configuration that end with P5. Iron, we would have to draw its orbital diagram. You are allowed to use a noble gas notation to shorten that electron configuration, even if it's an orbital diagram. And we have to draw the entire thing to be able to predict, well, how many electrons are unpaired. Well, if we draw the whole thing, we can see, according to Hund's rule, in this final subshell, we have 4 unpaired electrons. So the answer to that second question would be 4. Here are some more practice problems. Take a moment, try these yourself, pause the video, and we'll quickly go over the answers after you finish them. So for 6.68, we're determining the number of core versus valence electrons. So for our first element, anything that has a principal quantum number that is lower than the valence shell is a core electron. So my 1s2 electrons are core electrons. Everything that has a 2 next to it is a valence electron. All of my electrons that are in the sphere-shaped orbitals and the dumbbell-shaped orbitals are all valence electrons. For letter B, I know that my valence shell is my 3s2, my 3p5, or 3p3, I should say, 5 total valence electrons. Everything else is a core electron. And for letter C, my 1s2 is core, and my 2s2 and my 2p6, 8 total electrons are valence electrons. For 6.69, I'm just I'm writing the electron configurations for various elements. The one that I do want to point out to you is letter E. As we start to get into the F block, we have some weird things that start to happen to electron configurations that become very hard for us to predict. So sometimes even I have to go back to tables and refer back to that to see how we fill those actinides and lanthanides when we get to them. So that's the one thing I did want to point out, but you should have a very firm understanding of how to write the noble gas configuration for any elements in the first 5 periods at the very least. Our next topic is going to be periodic trends. We're going to be reviewing that, and we're going to be starting chapter 7. But that pretty much ends chapter 6, which was the properties of light, how light interacts with matter, and electrons in atoms.